We conducted stress tests on metals at varying temperatures. Our group members are Russell Hankey, Timothy Jordan, Mark Lewis, Scott Seebeck, and Maxwell Steffen. Throughout this presentation, we will first cover the background of our testing, which includes our inspiration, the theory behind our testing, and the currently existing literature. Then we will cover our method, which includes the experimental plan, procedure, required equipment, and our safety risk assessment. We will then discuss the results observed from our collected data and the uncertainty of them. Finally, we will report our primary conclusions, sources of error in our testing, and future work. The inspiration for our testing is to provide material strength data on metals that may be used for icebreaker boats. Icebreakers are used to break ice for ships that follow them, allowing for more direct paths to more places on the Earth. Icebreakers operate in constantly cold temperatures and must withstand substantial impact to their hull in the process of breaking ice, requiring the material of the icebreaker to be strong at cold temperatures. This leads to our key question for this experiment. How do cold temperatures influence the material strength and hardness of metals?
Are commonly used to show the relationship between stress and strain for materials and allows for material properties such as modulus of elasticity and ultimate strength to be graphically shown. Figure 2 shows an example of a stress-strain curve. Stress, shown as sigma in the equation 1, is calculated by dividing the force on a material by the cross-sectional area. The cross-sectional area is taken as a constant to simplify data collection and analysis. Strain, shown as epsilon, is calculated by dividing a new length by the original length. While it is commonly observed and accepted that metals become harder and have a higher modulus of elasticity and ultimate strength at lower temperatures, there are no widely accepted equations to model this behavior. Our goal for this test is to create a relationship between material properties and temperature through the use of stress-strain curves of materials at different temperatures.
Here you can see stress-strain curves at room temperature for 260 brass, 6061 aluminum, 1008 steel, and 1045 steel. Unfortunately, we had a difficult time finding stress-strain data for material tests done at cold temperatures.
Our experimental setup shown in Figure 3 includes the load cell, labeled LC, the load holders, labeled LH, the dog bone, labeled DB, and the heat exchanger, labeled HE. For our testing, there is also a cooler that runs on cold glycol through a heat exchanger, a thermocouple for measuring dog bone temperatures, and a computer that collects data on the force recorded by the load cell and the stroke of the load frame. The variables being measured were force, displacement, and temperature. Using dog bone geometry and force measurements, the stress and strain curves were generated.
The procedure that we use to conduct the experiment is as follows. First, the tensile tester environment is prepared and the heat exchanger is run at the test temperature. Second, the test specimen is placed in the external freezer and is cooled to the freezer's temperature. Next, the specimen is removed from the freezer and placed in the load frame. Once the specimen warms up to the test temperature, the load is applied to the specimen until failure is reached. The change in temperature, displacement of material, and force applied is reported for the duration of the test. From the recorded data, the stress and strain data is calculated for each material's dog bone geometry. Then the specimen remains are removed from the testing environment. Trials are repeated 3 times for each material at each test temperature. Lastly, the effects of temperature on strength and elasticity can be analyzed.
The equipment we used included an interactive instruments model K1-16 load frame capable of exerting 1,400 pounds with a load resolution of 0.1 pounds and a stroke resolution of 1/10,000th of an inch. The transducer technique model LPU-1K load cell on the load frame had a capacity of 1,000 pounds, a sensitivity of 3 millivolts per volt, nonlinearity of 0.1%, hysteresis of 0.1%, non-repeatability of 0.05%, and a zero balance of 1.0%. We used a Rockwell Model 3R hardness tester with a resolution of 1 HRB or HRC. To measure the temperature of the test environment, a Fluke 116 with Type K thermocouple was used that has a range of negative 40C to 400C, a resolution of 0.1C, and an accuracy of 1%. A Fisher Isotemp 306S refrigeration circulator was used in conjunction with our heat exchanger. A Danby chest freezer capable of negative 30C was used for initial cooling of the test specimens. We conducted our tests using 260 brass, 1045 steel, 1008 steel, 6060 and 6061 aluminum. Finally, we had safety glasses and gloves for usage in the lab.
We determined that this is a low-risk experiment. The test specimen's fracturing during the tensile test was a concern that was mitigated by wearing safety glasses and standing away from the test while it was in use. To prevent skin contact with the cold metal and heat exchanger, or the test specimens, gloves and long sleeves were worn with any interactions. Lastly, the antifreeze being used is toxic when ingested and as a skin irritant. While working with it, gloves would be worn and steps would be taken to prevent ingestion.
Our data for the 3 trials of 260 brass at room temperature, 15 degrees Celsius and 5 degrees Celsius. We plotted all 3 trials at the top of each figure. Then at the bottom of each figure, the average of the 3 trials are plotted with error bars. The error bars are relatively small with somewhat larger variation on the laches region. The overall trend of the ultimate stress is that as temperature decreased, the ultimate stress increased. These figures show our data for the 3 trials of 1008 steel at room temperature, 15 degrees Celsius and 5 degrees Celsius. We plot all 3 trials at the top of each figure, and at the bottom of each of the figures, the average of the 3 trials are plotted with error bars. The ultimate strength of the test specimens increased as the temperature decreased, with a model equation shown on a later slide. The error is relatively small, showing little difference from each test with the average.
These figures show our data for the 3 trials of 1045 steel at room temperature, 15 degrees Celsius, and 10 degrees Celsius. We plotted all 3 trials in the top graph of each figure. Then in the bottom graph of each of the figures, the average of the 3 trials are plotted with error bars. The ultimate stress did increase as temperature decreased from room temperature to the colder temperatures. However, this data cannot be used to determine by how much the ultimate stress increased. This is because the ultimate strength became higher than the force the load frame could generate and the load cell could read when the dog bone was cooled to 15 degrees Celsius or lower. Take note that the error bars have larger variation along the elastic region of the stress strain curve, with small variations occurring closer to the ultimate strength. These figures show our data for the 3 trials of 6061 aluminum at room temperature, 15 degrees Celsius and 10 degrees Celsius. We plotted all 3 trials in the top graph of each figure, then in the bottom graph of each of the figures, the average of the 3 trials are plotted with error bars. The third trial for aluminum at 15 degrees Celsius broke sooner than expected, most likely due to a material imperfection or material error. If the data from the third trial for aluminum is ignored, the ultimate strength trend would be linear, with the ultimate strength increasing as the temperature decreased. The error bars for aluminum were the largest and most significant. Because of the outlying third test at 15 degrees Celsius, the residuals were much larger. The error bars, like with other metals, were larger along the elastic region of the stress strain curve, with small variations occurring closer to the ultimate strength.
At the top of each of these figures, we can see the average graphs for each temperature in the same figure for each metal. At the bottom of each figure, we can see the literature data at room temperature for the corresponding metal. For 260 brass and 1008 steel, we can clearly see that the ultimate strength increases for a decreasing temperature.
At the top of each of these figures, we can see the average graphs for each temperature in the same figure for each metal. At the bottom of each figure, we can see the literature data at room temperature for the corresponding metal. For 1045 steel, the ultimate strength seems to increase for decreasing temperature, though there are clearly problems with our test for lower temperatures. For the 6061 aluminum, the samples did not seem to be consistent, causing the data we produced to show an inconsistent relationship with temperature.
These are the equations of best fit generated using the data. The Young's modulus best fit is parabolic, and thus more tests should be done at intermittent temperatures to get a more accurate curve fit. In addition, more tests should be done at the current temperatures. The ultimate stress model for aluminum is also parabolic when it was expected to be linear. The test for 15 degrees Celsius for aluminum broke much faster than expected, possibly due to a machining error or a material imperfection.
As you can see from the table above, there is the trend seen before where the ultimate stress increased with a decrease in temperature. For all of the above uncertainty calculations, the multivariable calculus method was used to determine uncertainty due to the inaccuracies of the various measuring instruments, such as the load cell and the digital calipers. The calipers, and thus the area and dimension measurements, had the largest influence on the uncertainty, because the values of the sensitivity indexes for the width and thickness were significantly larger than that of the sensitivity index of the force.
We observed in the findings that there was a slight increase in the ultimate strength for 2060 brass, 1008 steel, 1045 steel, and 6061 aluminum. The results found did not match the literature reviewed exactly. The ultimate stress was slightly higher in the literature than in the test performed. This difference leads to the conclusion that there is a high error that occurred in the repeatability of the tensile test. The trend of the Young's modulus seemed to be parabolic with the change in temperature. Not enough data was collected to make a truly accurate model of Young's modulus changing with temperature.
Due to how little material makes up the dog bones, the temperatures of the material rapidly increase due to the ambient air temperature. Therefore, the lower the temperature the test was performed, the faster the temperature changed during the test and the less accurate the data. A chamber was experimented with to keep the ambient air cooler around the dog bone, but it was determined to be ineffective. The test needs to be performed quickly due to the heat exchange of the dog bone, so the thermocouple may not have had enough time to cool down to the same temperature as the test piece. Also, the dog bone cools quicker in the middle where it breaks, so there is some difference between where the thermocouple is placed and where the dog bone fails. While a load cell is rated for 1,400 pounds, the frame can only provide a maximum of 1,000 pounds of force. Since some of the dog bones needed over 1,000 pounds to break, some of the data plateaus, resulting in difficulty finding actual ultimate strength.
We would like to thank Dr. Carl Hoover, who provided the lab equipment and materials necessary for this test, as well as useful suggestions on designing our heat exchanger. We would also like to thank Sandeep Kadka, who helped us to stay on track and provide helpful suggestions on the types of tests we should conduct. These are the references that we used during our project.